Today, I'm going to talk to you about one of my favorite math problems. It's simple and easy to understand and doesn't require much previous knowledge. We have a certain number of coins on the table. Let's say you put half of them and your opponent put the other half. And you're going to play a two-player game. On each turn, you can remove one, two, or three coins from the table. You choose, and the person who removes the last coin gets to keep all the coins. Do you think you could always win? Well, the general idea is to always look at the end of the game. If, on your turn, there are only one, two, or three coins, then you win, because you can just remove the exact number of coins at the end of the game. But if there are four coins left on your turn, you lose, because no matter what you do, you'll leave your opponent with one, two, or three coins, and they can win. So, your goal is to make your opponent face four coins, not you. Basically, if you want to win with 12 coins, you need to win with 8. And if you want to win with 8, you need to win with 4. And we already saw how to win with 4. So, the second player always has a winning strategy. Basically, no matter what the first player does, the second player can take the rest. So if you're the second player, you can guarantee you win. So what's the winning strategy? Well, by always leaving a multiple of 4 coins on the table. Let's say A is the first player and B is the second player. So if A removes 3 coins, B removes 1 coin. If A removes 2, B removes 2. And if A removes 1, then B removes 3. And B always brings the total down to a multiple of 4. And B can always do this, while A always has to play from a multiple of 4. That's because if it's your turn and the number is a multiple of 4, you can remove enough to reach another multiple of 4. You always leave a winning position for your opponent. And the goal is to reach 0, which is a multiple of 4. So if it's always a multiple of 4 at the end of B's turn, the final 0 will also be at the end of B's turn. And player B will always win. Now, what if instead of 12 coins, we use 13 coins? Well, now the first player wins, because they can just remove 1 coin, and now they are the second player in the 12 coin game. So, now, what if we have n coins? So, a random number of coins. It's actually not that hard to generalize. It's the same idea. If n is a multiple of 4, then B wins. If n is not a multiple of 4, then A wins. And with that, you can win the game every time. You can even let your opponent choose whether to go first or second. And depending on what they pick, you can secretly choose the number of coins. This game is called NIM. It's well known in the math community, and there are many generalizations. It's also a great introduction to game theory. So now I'll give a more general explanation of why this strategy works. Basically, the idea is to analyze winning and losing positions. Every position is either winning or losing, because there's no randomness, and someone must win. You always have to remove at least 1 coin, so the game must eventually reach 0. Basically, a position is winning if the player whose turn it is has a winning strategy. It's losing if no matter what the player does, the opponent has a winning strategy. Here, 0 is a losing position. If it's your turn and there are 0 coins, your opponent already won. Then 1, 2, and 3 are winning because you can always move to a losing position, which is 0. 4 is losing because every move from 4 leads to a winning position, 1, 2, or 3. And then 5 and 6, 5, 6, and 7 are winning because they can move to 4. 8 is losing because every move from 8 goes to a winning position, which are 5, 6, and 7, and so on. We can do this process infinitely, and we can see that there's a clear pattern. So this position matches what we saw earlier. Multiples of 4 are losing positions for the player whose turn it is, and the others are winning. Now, what if instead of removing 1, 2, or 3 coins, we remove, let's say, 2, 5, 6, or 10 coins? What are the losing positions for the A player, so the first player? Well, let's analyze it. 0 is a losing position because you lose. 1 is also losing because you can move. 2 is winning because you can go to 0. 3 is winning because you can go to 1. 4 is losing because the only options are 2, which is winning. 5 is winning because you go to 0. 6 is winning because you go to 0. 7 is winning because you go to 1. 8 is losing. You can only go to 6, 3, or 2, and all are winning. 9 is winning because you go to 4. 10 is winning because you go to 0. 11 is winning because you go to 1. 12 is losing because all the moves go to winning positions, which are 10, 7, 6, and 2. 13 and 14 are winning, and we can keep going infinitely with all the numbers. Eventually, we'll see a pattern. In this case, it's a pattern of length 15 that repeats forever. Why? Because each result only depends on the previous 10 numbers, since we can remove at most 10 coins. And once we see one repeating segment, the next will be the same, and so on. So now we know who wins in each position with 15 coins. If you're in a winning position, just move to a losing one. That's your strategy. And that's how you can always win. So, now you solved every possible single row nim. For any set of allowed moves, you can follow this same process to find winning and losing positions. If the set is finite, there will always be a repeating pattern. And this strategy works for any amount of removable coins. Thank you.